Okay, the other kind of stereoisomerism besides easy cis-trans isomerism is optical isomerism. And optical isomerism occurs when a molecule contains one or more chiral carbon atom. Chiral carbon atom, so that's a new term. A chiral carbon atom is a carbon atom that has four unique attachments or four unique groups or atoms attached to it. It comes from this term chirality, which has to do with the Greek term related to hands. And what we end up with when we have optical isomers is we have molecules that basically act like they are left and right hands to each other. It's an analogy, but it's a pretty good one, because if you think about your hands, each hand has four fingers and a thumb attached to the palm, or at least hopefully it does. And for all intents and purposes, your two hands are the same. You would describe them as four fingers and a thumb attached to a palm. But if you try to put your two hands on top of each other, you probably know from experience that they don't line up. The thumbs are sticking out in different directions, so they're not exactly the same. Even though if you describe them and just looked at them quickly, they do look more or less like they are the same hand. So molecules can be the same way. These carbons in the drawings here are chiral carbon atoms. So a simple example, each carbon has four different atoms attached to it. And so these molecules, if you first look at them quickly, they might look like they're the same. But if you imagine taking the one on the right and trying to rotate it around, spin it around here, when we do that, the Cl would still be pointed up, the Br would now be pointed this way, but the F would be pointed back here, and the H would be pointed out here, right? So because the H is on this side of the F. So as the F goes around, the F would go to the back, and the H would be around here. And so you'd end up with F, and you'd end up with H. And that's different than HF, like in that molecule. So this will be easier to see in class when we can actually play with the three-dimensional models. But what I'm trying to show you in these two drawings is that these two molecules are not the same molecule. They actually are slightly different. They are mirror images of each other, but they're not actually the same, and they're not superimposable. So I can't put one directly on top of the other one and have it be exactly the same. So the relationship of these two molecules, the term for them is enantiomers. So they are non-superimposable mirror images of one another. So that's what happens when we have a chiral carbon. We can end up with this is when we have a single chiral carbon. We end up with two molecules that for all intents and purposes look the same. They have all the atoms are attached to the same atoms, and they are mirror images of each other, but they're not actually the same molecule. They are non-superimposable mirror images of each other. Okay? Now, the way to represent these with what's known as the dash wedge structural formula is trying to indicate some sort of three-dimensionality to the molecule. So if I take that example above, when we draw a dash wedge, usually you draw, well, maybe I'll do it the other way. That's kind of how this one is drawn. I tend to draw the dash and the wedge going in towards the center. So the idea is that the dash is sort of fading away from you, whereas the wedge is coming out of the screen towards you. The simple regular line segments, like to the Cl, and I'll draw, I guess, to the Br, if I flip it, those are meant to be in the same plane as the board or the page or the iPad screen right now. Okay, so what I'm going to draw over here is one way of drawing this molecule. So in this drawing, I'm trying to indicate that the hydrogen is kind of going back into the page, and the F is sort of sticking out at you from the page. And it should indicate pretty well this tetrahedral geometry. Now, the way to draw the other enantiomer is pretty easy. It's helpful to draw a dashed line. It's sort of like, that's like the mirror. Think of that as the mirror plane, and now you're going to reflect it in the other side of the screen. So all you have to do is literally reflect it. So here's H and F, put them in the same positions, Cl and Br, and then you treat them exactly the same. Give the same atoms those lines, and then give the same atoms the dash and the wedge. And now you've mirrored that molecule onto the other side. So this is how you draw enantiomers on the IB exam. they ideally want you to use the dash-wedge structural formula, which indicates some three-dimensionality, and then you just reflect them. And I recommend drawing that dotted line to represent the mirror plane. Okay, so you may ask, what's the point of this kind of isomerism? At first, it seems really like insignificant. These molecules are going to behave exactly the same. And in many ways, they do. They really don't have different physical properties in terms of boiling points or melting points. They have the exact same IMFs because their orientation is just inverted, but really overall, it's the same. The only difference that they have in a physical property is the way in which they rotate plane polarized light. And that's where this term optical isomers come from. It's how we can tell them apart is using something optical, using something with light. We're going to come back to that in a separate video. Okay? So that's their only distinctive physical property from one another. Now, chemically, in typical plain old boring chemical reactions like we've done, sorry, not boring, but normal chemical reactions, they have the exact same chemical properties because they have the same atoms and they're more or less oriented the same. So usually they have the same chemical properties. When they don't have chemical properties is with other chiral substances, other things that display optical isomerism. So they have different chemical properties with other chiral species. So we use this term chiral. We can describe things as being chiral if they will also display this kind of isomerism, this optical isomerism, the different hands. And the body and nature are amazing at this. And in nature, a lot of molecules only exist, only one of the enantiomers exists and is produced naturally. And the other one can be easily made in the lab, but naturally it won't exist. And some classic examples of this are amino acids. Amino acids are all one hand. In nature, we pretty much, glucose is pretty much always in its D or right-handed form. And when it forms a ring, alpha glucose is the type of glucose that makes up starch, which is a main food source, energy source for humans. And beta glucose is what makes up cellulose, which is dietary fiber, which we cannot digest. And so the only difference in orientation is that these are basically enantiomers of one another. And that subtle difference in orientation is actually enough to make them have completely different pathways in how they can be used by the body. And I think of it as a lot of reactions that take place in the body have to do with molecules fitting together in a certain way, like molecules fitting with receptors. And if you think about your hands and gloves as an example, an analogy of this, you have a left-handed glove. Here's my beautiful left-handed glove. That's really only going to fit with your left hand, right? So that will fit nicely. If you try to take your right hand and fit it into your left-handed glove, you know you could probably force it, but it's not a very good fit because the fingers don't line up in the right positions. So that's kind of how the molecules work as well, especially in biochemical situations. They need to have the exact right orientation for them to fit well. And if they don't have the exact right orientation, they don't fit as well, they don't trigger the same kind of response. And we see this in a lot of different biochemical processes. So chirality is super important biochemically, and in nature, it can have some distinctions in chemical properties with other chiral species. So the reason why it has so many differences in biochemistry is because so many biochemical species themselves are chiral. And so all these different chiral handed things are fitting together in unique ways, and so it has a major impact. So in terms of this topic, the main thing is being able to draw enantiomers, knowing the distinctions in their properties, and then being able to spot chiral carbons. So in these molecules, for example, it helps us see maybe some more distinctions in this topic that you wouldn't have otherwise realized. Okay, so like in serine, this is an amino acid. This is a simple example. If you're going into this molecule here and you want to identify the chiral carbons, the carbons need to have 4 unique attachments. So as soon as you see that like this carbon has 2 H's on it, that carbon can't be chiral because it already has 2 of the same thing attached. We don't worry about nitrogens or oxygens. They don't have enough things attached to be chiral, so we're only looking at the carbons. This carbon, COOH, I know is a double bond and then an OH. So this carbon actually only has 3 different attachments, right? It has a carbon atom to its left, it has a double bond to oxygen, it has an OH group, so this can't be chiral. This carbon in the center is chiral. It has an amino group to the left, it has a CH2OH group down here, and it has a carboxyl group here, and then it has a hydrogen as its 4th attachment. So this carbon atom there is chiral, so that's a chiral carbon. Now that's kind of the most straightforward type. If we look at D-glucose, it actually has a number of chiral carbons. So all these spots within these line segments, those represent carbon atoms. And every single one of those purple carbon atoms that I just drew is chiral. If you think of the top one here, it has an H, it has an OH, it has this aldehyde group here, and then it has the rest of the chain. So that represents 4 distinct attachments. So even though in 2 directions it has carbon atoms bonded to it, you have to look at the whole group that is attached in either direction. And if those are different, it makes that carbon atom chiral. If I erase this and look down at the next example, this one has this group, this group, this group, and this group. So those groups are all distinct. So this carbon atom is also chiral. And if you move down the chain, all of these carbon atoms in the middle are chiral. Now this one isn't because it has 2 H's, and this one isn't because it only has 3 attachments. So those are quick ways to get rid of carbons as options, but the D-glucose has 4 chiral carbon atoms. And just one more, if we're going to let's look at ibuprofen. And this is from the data booklet, so it's sort of this mixed skeletal type structure. The thing with the ring in it, the hexagon, is a benzene ring, a phenyl group, and all of those carbons must have H's out of them because carbon needs 4 bonds, and the benzene ring itself gives them each their 3 bonds from that delocalized electron ring. Now we're looking for carbons with 4 distinct attachments. None of the carbons in the benzene ring, or the phenyl group, are going to be chiral because they only have 3 different atoms attached to them, so they can't be chiral. We can get rid of ones with 2 or 3 H's attached. Those can never be chiral. And things with double bonds off of them because they'll only have 3 atoms attached. So I'm left with 2 carbons to choose from, really. Now this carbon is not chiral because it has a methyl group and another methyl group. So 2 groups that are repeated. If you have 2 groups repeated, then you won't have this kind of isomerism. And so I'm left down here with this carbon atom. It has a methyl group, an H, a carboxyl group, and it has this whole other thing sticking off of it, this whole rest of the molecule. So that's a chiral carbon atom. And we also have to look at things in the rings. So thalidomide was a drug molecule, we'll talk about it in class, probably the most famous example of chirality, and of chirality ignored, and the really dangerous consequences that that can have biochemically. So there's only 1 chiral carbon atom in thalidomide. And we go through here. These are all carbons in benzene rings, so only 3 attachments. None of those are chiral. These are carbon atoms here, but they are double bonded, only 3 attachments, so not going to be chiral. This is a nitrogen, we don't have to consider that. And then if I go in and fill in these carbon atoms here, these 2 are out from the double bonds. These 2 only have 2 bonds, so they must have 2 H's off of them, so they're out. And that just leaves this carbon atom here, which has 3 bonds shown so far, which means the 4th bond is to a hydrogen atom. Now, it's a bit of a funny one because it's in a ring, but it actually is considered to be a chiral carbon. So it has the H, which is 1 attachment. It has this whole thing, which is another attachment. And then it has these 2 different directions of the ring, and they're not symmetric to each other. So like this half of the ring is actually considered sort of a distinct detachment from this half of the ring. And you can have alternate orientations. Well, you can have the other hand orientation of that ring or of that thalidomide ring. So this carbon atom here, although it's probably not one that would have jumped out at you by the definition, 4 distinct attachments, that is a chiral carbon within thalidomide. So we'll talk about it more, but chirality, when we have these chiral carbon atoms, carbons with 4 distinct attachments, and that can take many different forms, as we've seen in the examples down here. When you have a chiral carbon atom, that means molecules can exist as enantiomers, or these non-superimposable mirror images, which for most simple chemical and physical properties are identical, but they have distinctions in how they will rotate plane polarized light, and they react different chemically with other species that also have chirality.